Yeah.
Okay, everyone, welcome back. So let us have our second lecture of this morning. Okay, please take it away.
Okay, welcome back. So let me first summarize what we've learned in the last lecture. This is basically the summary of the last result. If we have the S soft photons that are uniformly at the same rate taken to be softer than all the hard particles, then in scalar QED, the corresponding soft theorem looks like this. We have the product of the Weinberg soft factors multiplying the hard amplitudes to leading order. And as I mentioned at the end of the last lecture, this basically concludes our discussion of the real radiation, which is to do with the soft external particles. And what we're going to do next is focus on the virtual radiation. Okay, so recall that the virtual radiation refers to radiation inside of the loops. Okay, so we're going to kind of follow a similar path. What we're going to consider is what happens with the soft particle inside of the loop. First one particle, and then we're going to generalize it to multiple particles and see how they create divergences. Okay, so one of the options that we can have, I'm going to claim is the simplest option, is in which we have two external momenta. Let me call them Pi and Pj. And now there's a particle, soft particle of the momentum L that is somewhere in between. Okay, so what I'm going to use, the notation that I'm going to use, because now you see we have to integrate of the loop momentum L of the massless particle. I actually have to tell you what is the distinction between like what I call soft and what I call hard, right? So let me put this distinction on a scale of energy. And what I'm going to do is I'm going to create an arbitrary cutoff, lambda, capital lambda. And everything above this cutoff, I'm going to call hard by definition. And everything below this cutoff, I'm going to call soft, or soft. Okay. So the next thing that I'm going to do is I'm going to pretend that I have some scattering amplitude of n particles with the cutoff lambda. So I'm going to pretend that for this amplitude, I've computed all the complicated loops and all that is associated with hard states. And then what I'm doing on top of that is including the first correction from the physics of the soft particles, which in this case would be adding just one extra soft momentum. Okay, I'm going to claim that this is the leading order. And let's just write down some equations. So what I want to compute is first the contribution from this specific diagram in which I have the soft particles attaching, a single soft particle attaching between I and j. So I'm going to call it Sij. Okay, and then of course what I have here is the integration over the loop momenta. I have the soft particle propagator, L squared, which is massless. And then on top of that, what I have, well, some normalization factors. So for example, the 2 pi to the 4th power just comes from the measure of the integration and things like that. And now the work that I have to do is that I have to evaluate this contribution from this diagram. But you see, now there's this particle is internal, So I have to, in principle, sum over all polarization states of this particle. So when I write the integrand, in the integrand, I have the sum over the, or rather, helicity states, because it's massless particle, which could be plus or minus. And then, just like we've seen before from the Feynman rules, I essentially have the polarization of the particle with the, so this particle here is going to have polarization epsilon. Let me introduce the label H to denote the helicity, dot pi, right? And downstairs, I'm going to have L dot pi plus I epsilon. And from the second factor, I'm going to have the J contribution with minus the helicity, because the helicity is viewed as incoming from one perspective, but outgoing from the other perspective, dot pj, and then L dot pj plus I epsilons. Okay. Now, this distinction here, this minus sign and this plus sign in here comes from the fact that when I attach to vertex J, I basically have the same map, the same Feynman rules as before. But now, when I attach to this leg here, the momentum that is being attached from the all incoming conventions is minus L, not L. And that's the origin of this minus sign in here, just the orientation. Okay, and now what I also have to specify is whether the momenta I integrate over. So I already, by definition, I agreed that I'm going to only include the momenta of the soft modes, which are the ones below the capital lambda cutoff. However, just by power counting of this integral, we can count how many powers of L we have, okay? So we have D for L, and downstairs we have L squared, something linear in L, and something linear in L. So overall, I have 4 powers of L in the numerator and 4 in the denominator. So this means that this integral is actually divergent. So this means that this, if I just integrate it over this, it's not going to give me a sensible answer. Instead, what I have to do is introduce a new cutoff, lowercase lambda, and this is going to be my infrared cutoff. Okay. So let me summarize. The capital lambda was just our arbitrary distinction between what I call soft and hard. And now our lowercase lambda is an actual cutoff. I'm saying I'm not integrating over anything below that. And the idea is that I'm going to do the computation in this setup, so including all these soft modes in here. And then at the end of the computation, I will try to take this lowercase lambda all the way to 0, which is going to be my limit of probing long-range physics being exchanged in the loop. Yes. Yeah.
Which depends on the area.
Should we include? Okay, sorry, can you repeat?
We have the rest of the amplitude. Right?
Yes.
M particle.
Yes.
And in this case, it also depends on L.
Yes. Sorry. So let me just clarify. Yeah, excellent question. So what I'm going to do is I'm going to write this contribution. Sorry, I forgot to write. I'm going to write it as Sij. Ij just labels which specific diagram I'm considering, times the rest. Okay? So all the rest here can include all the hard stuff included inside of the loop. And once again, this is only going to be the most relevant contribution in the soft limit.
But then in this leading contribution, we can have immediate dependence of L in the
Yes, I'm going to pretend that this object here depends on the L implicitly. Yeah, that's right. But then ultimately, the most important part is going to come from L equals 0, the soft limit. And in that limit, we can pretend that this is on shell. Okay, so that means that the incoming particles just inherit kinematics from the incoming particles of the external states. Okay, any other questions? Does it answer the question? Okay, so let's just do this computation. Perhaps the most scary object here is the sum. But as I mentioned, what we're going to do is we're going to localize essentially on taking this particle to be on shell. So sometimes we would draw it as a cat. Okay. And what this means is that in the on-shell limit, performing the sum is actually very, very simple. So the sum over epsilon h minus h can be replaced with epsilon mu plus ... where the contributions from the ... decouple in the masses in the on-shell limit. Okay, so what this means is that I can essentially use this sum here as a glue that is going to combine these factors and these factors, and then simplify this expression. So let me do it. Let me try to do it here. Okay. So there's going to be minus I, then the charges EI, and then EJ. Then this, the minus are decopied, and then this is going to contract PI and PJ, which is a constant from the perspective of the integration. And then I have the normalization. All right. And then in the end, what I have to do is I have to do a 4-dimensional integral over L squared with I epsilons, and then this and this. Right? In the preparation for the next step, what I'm going to do is, in fact, split this 4-dimensional integration into the energy component and the spatial component. Okay, and remember that there's a limit on this integration, which is this one. Okay, I should say that there's many different infrared cutoffs. For example, a common one is dimensional regularization, which essentially works in a similar way, although technically the calculation is slightly different. I'm going to commit to this, what people call the hard cutoff, which is not the most practical one in general, but at one loop, it teaches us a little bit of physics, so I'm going to stick with it. Okay, so let's now try to evaluate this integral. Yep.
So we're still integrating over the whole domain while still assuming that the integral is dominated by the on-shell region so that we can use the projection. How do we know that this is consistent?
So the question is, how do we know it's consistent to perform this projection? The most honest answer is that you could have kept the additional terms and then you could have repeated all the steps all the way, and then you would have seen that eventually they decoupled. So I just wanted to make a small shortcut in here.
Can we use that sum for reality?
Yes, with the additional terms. Yeah. All right. So what I'm going to do is I'm going to first try to evaluate the energy component of this integration, which turns out to be very simple. And then I'm going to, I'll tell you a little bit about the rest. Okay, so what this means is that first I wanted to understand what happens in the complex plane of L0. Okay. So first of all, in the complex plane of L0, I just have to integrate of the real axis in here. Okay, but now it's obvious that the integrand here has some singularities. There's two singularities corresponding to this factor, one from here and one from here. So there's going to be 4 poles in general. Okay, so now it's very important that we keep track of all the factors of I epsilon, because they actually tell us important lessons about how these poles are being displaced. Okay, so as usual, there's going to be this pole in here and this pole in here that come from this factor. And now there's going to be one pole from here. Okay, so let me use the notation. Let me say these ones I'm going to denote with white dots. These ones are going to be denoted with crosses, and these ones are going to be denoted with black, or maybe I should say green dots. Okay, so in this convention, there's going to be a pole somewhere here. Is there a question? Yeah. Yeah. Yes, thank you. There's a typo here. An obvious one. Yeah. Okay, good. So we see that this is just locating the pole of this factor. So we see that the I epsilon for this factor is I epsilon divided by the energy of the ith particle. So the energy in our conventions could have been positive or negative, depending on whether it's an incoming state or an outgoing state. Okay, so this means that I actually have to distinguish between different cases. This case is going to be the in case, in which both Pi and Pj are going to be incoming and incoming. Okay, so then this is positive, so then this is positive, so we have it in the upper plane. There's going to be a very similar picture for the other case. Let me call it in-out. So I'm going to do these two cases, and I'm going to leave out-out and out-in as a simple exercise. Okay, so in those cases, nothing happens. The poles of the first factor are the same, but the cross now I have to put on the other side of the real axis. Okay, and then finally I have the green dot, which in this picture is going to be somewhere here. See, the nature of the I epsilon changes because of this minus and plus. Okay, so this one is going to be at L dot Pj minus I epsilon divided by Pj0. Yep. And actually, sorry, to be consistent with my notes, this is the case in which Pi0 is positive and Pj is positive. In this case, let me call it Pi being positive and Pj being negative. So actually, in this case, there's going to be a cross here and a white dot, green dot in here. Okay? Right. So now we've identified the singularities, we have the integration contour. And when you see something like that, as a theoretical physicist, something should really be very pushing you towards doing something with this contour, right? What can we do with this contour? We can deform it. Okay, so what are some ways in which we can deform the contour? Well, we can either push it up or push it down. Okay, it's clear that there's not going to be anything at infinity. So essentially, let me choose the option in which we deform it down. So that means, in this case, we just pick the residue on this pole. And then in this case, we would pick the residue on this pole and this pole. Okay, so you see that naively, at least, there's a distinction between whether the particles are incoming or outgoing. We seem to be picking up either one contribution or two contributions. Okay, so let me, the next step, well, you can, this essentially takes care of the L0 integration. I have to do the spatial integration on top of that. I'm not going to torture you with going through all the steps. Let me just tell you the final answer. So as I mentioned, the final answer is going to depend on whether we consider in-out or in-in case. So in-out is going to correspond to the picture that we drew at the beginning, something like that. And then in this case, there's going to be one term given by this residue, and I'm going to call it EI, EJ, just from the prefactors. Okay, so that's the answer, where the Rij is some function looking like this. Okay, with sigma ij simply denoting pi dot pj divided by the masses of the particles. Okay, so you can work out that in the case in which pi and pj are incoming and outgoing, this dot product has to be negative. In fact, this dot product has to be below the allowed kinematics. So if you work it out, it has to be below -1. So pi dot pj has to be smaller than mi dot mj. Okay, and then one thing that you can do is you can actually plot how this looks like. This expression here that I called Rij. The most obvious fact about this function is that it's real. In fact, that's why I called it R. And then you can also work out how it looks like when sigma ij is below -1. Okay, so for example, this is positive. With slightly more work, you would find that this is positive as well. So this Rij is positive. All right, and what this means is that in, well, this log here is positive as well, because the cut of lambda is always above smaller lambda. Okay, so what this means is that this Sij only is given by a product of a positive thing, and then Ei, Ej is actually negative. Right, because one is incoming and one is outgoing. In my conventions, this means one has a positive charge and the other one has negative charge. Okay, so this was the case of the in and out. And I should probably emphasize that this log is exactly, I mean, the log comes from the fact that this integral was like a scaleless integral, d4l divided by l to the 4. So it has a log divergence from the lower limit and log divergence from the upper limit. Okay, so this was the in-out case. Now in the in-in case, we're basically going to get the same term that came from here. We're going to get the same term, but plus something extra. So I would actually invite you to do this computation. So in this case, Saj is going to be equal to EI EJ. Okay, just the same contribution plus something extra times the log. All right, with this extra factor here, while this one turns out to be purely real, this one is purely imaginary with multiplying with I. Okay, and the I is equal to minus I pi sigma ij divided by the square root. Okay, where sigma is the same as before. But now, because we have the incoming state and the incoming state, the p dot p is positive and larger than m times m. So this means that sigma is actually greater than 1. Okay. There's actually a small, first of all, any questions about this? There's actually a small subtlety. So you see that the in case actually includes the case in which the particle attaches to the same external line. This term is slightly more difficult to work out. Let me just tell you the final answer. So what I'm saying here is that the diagonal term, RII, is the one in which the particle attaches to the same leg. This one is slightly more subtle because you have to renormalize it, and there's some subtleties here. But the net of this analysis is that you can actually just take the limit on this expression in here, in which sigma just goes to 1, and this is the correct answer. But for the imaginary part, you set it to 0. Okay, so that's related to renormalization. Okay, excellent. So now we can put all of this together. Okay, we basically obtain, at one loop, we're going to obtain a soft factor that is going to be obtained by summing over all these contributions of the diagrams in which I attached between leg I and j. I have to sum over all I and j, of course. But then I would be actually overcounting because this is symmetric in I and j. So I have to actually include a factor of 1/2 to compensate, to not overcount. Okay, and this actually gives me a factor of this type. Oops. In which the only thing that I have to do is distinguish between the two cases. One case is in which the energies of the particles are the same. So this is the one in which we have either in, as we've done over there, or out. And in this case, I have the imaginary part, and otherwise, I do not have the imaginary part. This is a step function. Yes?
In case of I equal to j, this will not be divided.
Yes, so this is included in this definition. Yeah, exactly. Yeah, excellent. So then the question is about the analytic continuation. So one thing that could bother you when you see an expression like this is that if you know anything about scattering amplitudes, you probably know that scattering amplitudes are supposed to be analytic functions of the momenta. So from that perspective, this actually looks horrible because it has a step function which is highly non-analytic. So the question is, can you actually combine this into a single analytic function and kind of unify the in-out case with in-in case? And this turns out to be possible. In fact, this leads me to the next step. The way that people would write it is, well, maybe you can recognize here, if you're good with your logarithms, you would recognize that this function here, roughly speaking, it has a discontinuity. This continuity of the log is I pi. So that function here, I pi sigma, looks like it's precisely the discontinuity of the above. And what I'm going to write down is essentially the way that makes this manifest. In fact, here I'm going to use what is very conventional in the literature is actually avoid writing these diagonal terms altogether. And instead, write it as this function called gamma cusp. Okay, so the gamma cusp is known as the cusp anomalous dimension. Okay, and then essentially it does, the role of a gamma cusp is to do what I said before, basically unify all the cases. And all of this amounts to a very simple operation in which before I had a log of the absolute value, the only thing that I have to do is actually remove this absolute value, and this automatically unifies both cases. So what this means is that if I now draw it in the complex plane of sigma, if I draw the dependence of this gamma cusp, you can see that it actually has a branch point at sigma is equal to 1 and a branch cut. Okay? Naively, it might look like it is a branch point at sigma equals -1. But then one thing that you can do is evaluate the log of -1. So this gives you 0 and +1, and log of 1 is equal to 0. So the additional singularity actually is not there at -1. Okay, and then this essentially unifies the two cases. This was the case in which the two particles were between in and in state. And this is the case in which the particles were between in and out states. Okay. Okay, so this fact that we can do the analytic continuation between these two different cases is related to the property called crossing, which is very interesting, and it goes way beyond the infrared divergences, and I would be happy to discuss it after the lectures. Why is what? the question is, why is there singularity at plus 1?
Minor first one. Yeah. The actual plus 1.
Why is there plus 1?
Yeah.
Oh, yes, sorry. So the plus 1 is the one thing that this is actually an interesting exercise to go between this line and this line, remove these diagonal cases. So you can show by momentum conservation, by charge conservation, that I can actually absorb these diagonal cases into the definition of the gamma cusp, and it works out to give you this additional plus 1. Very good. Yep.
Considering the case, because naively it would seem that there is an extra leg, extra internal propagator that becomes outshot this case.
Yeah.
Where, like, at which step is that taken care of, or?
So this is the question is about the diagonal cases. Here I slightly cheated. In principle, you have to do a very careful analysis, but this case is very, very special because it has to do with wave function renormalization as well. And there's a rather lengthy analysis that you have to do to actually work out that it works out to be this and this. Here I just told you the answer. Okay, I can give some reference in which people worked it out carefully.
So basically, that extra divergence is also being regulated by
This extra divergence just contributes the additional -1 here. It is a divergence because I have 1 times this, right? So it's still there.
Because it would seem there would be some kind of pole type of pole divergence instead of log.
Yeah, so here's where we would need to go for the more careful analysis. Yeah. It's going to be a log because it comes from a loop, no matter what. The loop is going to be, something attached here. It's a bubble integral. It's going to give you a log, but to actually work out that its log gives you this +1, not +7 or 13, you have to be careful. Okay. So now, since I'm way behind time, let me just summarize the whole story. So in principle, we could have repeated, if we had more time, we could have repeated all of this analysis at 2 loops, at 3 loops, and so on and so on. It's actually a very cool exercise. So the result of doing all of this is going to give us the new scattering amplitude in which I move the cutoff, which used to be at the upper cutoff used to be capital lambda. Now, including all the soft stuff, is going to move the cutoff to lowercase lambda because I essentially included more states. Okay, so to leading order. Well, the leading order is very simple. This is the one in which there's no soft momenta. And then what we worked out just a second ago is this capital S. That is the leading contribution from the one loop. Okay. We have not discussed subleading pieces. And then perhaps you can trust me following the or derivation of the multiple soft theorems in the real case. A very similar story happens here, in which when I include the 2 soft photons instead of 1, basically the only thing that happens is that I get a square of the original factor, and I also have to avoid overcounting because now inside of the loops the photons are indistinguishable. So I just avoid overcounting by including this factor. Okay, so this would be the leading 2-loop contribution plus the dot, and perhaps we can already anticipate the pattern. well, from the name of the section, what we're going to get is an exponentiation. Okay, so the answer to this is going to be the original amplitude times the exponential of s. And actually, strictly speaking, what we've done in here was studying the leading case, meaning the leading logarithmic part of the exponentiation. But you can show with much more work that was done back many decades ago, is that this turns out to be exact to all orders. This is a special thing about QED, and for example, it does not hold in QCD. All right, so now we can move on to the next topic. The topic is going to be a question that we've all been waiting for. So all of this is because we wanted to analyze the finiteness question about the scattering amplitude, right? So now we can ask the question whether the result is actually finite. Okay, so let me just expand, kind of summarize and expand at the same time. Okay, so this formula is going to tell us that we have the exponentiation. Exponentiation is going to have two pieces. Okay, the first piece is going to have logarithmic exponentiation times the r, the real piece. And the second piece is going to have the I piece, like so. Okay. Okay, so we have a factor that oscillates and a factor that gives us either a suppression or divergence. Okay, so let's just identify, let's write down this here. You can work out that the factor of I, this one here, is always negative. Okay, so this means that this thing here is always negative. So there's no possibilities of cancellations between the sum, within the sum. And what this means is that it's unavoidable that when you take lowercase lambda all the way to 0, you're going to have an infinite oscillation. Okay, so the outcome of this analysis is that there's an infinitely oscillating phase also known as the Coulomb phase, in the limit as the lowercase lambda goes to 0. And that's the correct result. The interpretation of this result is that the Coulomb field that is being exchanged between the electrons, or in our case, between scalars, all the way to at infinity, well, the Coulomb field goes like 1 over r, right? But also the wave functions go like 1 over r. So it means that if you have wave functions of particles, they keep interacting with the Coulomb field all the way at infinity. So in a sense, the particles themselves, the electrons and positrons or scalars, are not asymptotic states. Okay, so that's the, let me not write it down. This is the interpretation of this phase. It's as if we forgot to include the interacting part of the Hamiltonian that keeps interacting even at long distances. Okay, now what about the other factor in here? Okay, so I already mentioned that R, the real part of the divergence, is positive, and this means that this whole exponent here is negative. Okay, so this is negative, and this is positive. So what does it mean? Well, it means that in the limit, when I take lambda to be 0, this exponential factor is an exponential suppression. Okay, so this means that this factor here is the suppression as lambda goes to 0. Okay, this is the correct result. Okay, so this is the correct result, and in fact, what this tells us is that if I looked at, let me strip away the oscillating phase. So for example, when we compute the cross-section, the only thing that matters, or the scattering rate, the only thing that matters is the absolute value of the matrix element. So for example, if I compute the Mn lambda, well, what we've learned here is that this factor here is always suppressing, so the right-hand side is always smaller. So we get this result. And in particular, if I wanted to compute the cross-section, so the cross-section is going to be the limit in which I remove the infrared divergence, and then I keep the matrix element squared. Well, as I keep decreasing lambda all the way to 0 and 0, to smaller and smaller and smaller, eventually this gets squashed by the log, by the exponential, and this gives me 0. Okay, so there's a question that you can ask at this stage. What's going on? I guess originally I was probably going to write a different question with a 3-letter acronym, but I decided to soften it and write what's going on. So let me recap what we've done. We've analyzed Feynman diagrams, and then we've seen that each individual Feynman diagram has a divergence. But then somehow the magic of the abelian exponentiation told us that all these divergences, in fact, exponentiate. So they go into the exponential of the argument of the exponent, of the exponential. And moreover, the more careful analysis of the sign told us that the exponential is, well, the sign is negative, so it's the exponential suppression. So we went from analyzing what we thought are divergences, but we ended up finding out that the cross-section, as a consequence of those divergences, the cross-section is equal to 0. So what's going on? Okay, any suggestions? Excuse me? Soft photon what? Yes, that's the correct interpretation. So let me just repeat what you said in different words. Okay, so essentially what we computed here is what people call the exclusive cross-section. The word exclusive refers to the fact that both the initial and final states are fixed. Okay, so we went, for example, from 2 scalars to 2 scalars, and we included all the loop effects. But in a sense, this is not a consistent approximation because we included the soft virtual radiation inside of the loops, but we forgot about including at the same time the soft radiation coming from the real radiation. And this, in fact, brings me. Okay, so maybe let me kind of foreshadow what's going to happen. This means that basically what we've included is kind of a measure zero of all possible final states that we should have been including. So this gives us a zero. And the zero is essentially going to be multiplied by an infinity in such a way that 0 times infinity is going to give us a final answer. And that final answer is going to be the physical cross-section. All right, so let's see how far we can go. Okay, so this is the next part, including real radiation. Okay, so in a sense, what we're going to do is we've done this computation, in which case we've not done it explicitly, but I said in words that we've included all possible virtual stuff that build up our amplitude or cross-section. And now what we have to include is also the real stuff. So all sorts of radiation here, right? And now the interpretation is going to be slightly different. We can make a different interpretation, which is that we have this distinction between soft and hard modes. Now, physically, the way that you can think about this distinction is as a resolution of your detector. Okay, so you can say that the detector has a finite size. Because of that, it's not going to be sensitive to all the soft modes that are penetrating through it. So what this means is that we're supposed to think of it as missing certain parts of the soft radiation. And if the resolution of the detector is capital lambda, it means that we have to include the soft radiation coming from this strip, right? And only then we can take the limit of small lambda going to 0. So in a sense, what we've done so far is we've included the effects here from the loop stuff, but we forgot to include the external radiation. Okay, so let's fix that in the next step. And this leads me to the notion of inclusive cross-sections. Okay, so let me define what I mean by it. We're going to have some new cross-section with some cutoff lambda. This lambda is going to be the resolution of the detector. Now, the way that we're going to define it is that we're going to do what we've done before, which is we have this matrix element. Okay, it's a cross-section, so we square it. So this matrix element, because I called it lowercase lambda, this means that we've already included all the effects of the virtual radiation. And then on top of that, what I'm doing is including also soft radiation in the final state. So I'm going to assume that these S are only outgoing. All right? So after I've done that, what I have to do is I have to sum over the helistes for all of these soft particles. I have to sum over their helistes because I cannot distinguish between them. Then I have to integrate over the Lorentz invariant phase space of the soft particles. So there's going to be a Lorentz invariant phase space of S particles. And then, of course, I have to sum, as we've done over and over again, over the number of soft particles. And I have to do it in such a way that all of the momenta, let me call them K, of the soft particles are above the cutoff, but also in such a way that the sum is below the resolution of my detector. Okay, so this integral here has these conditions. All right, so let me decide how much we can finish today. You know, let me just do it quickly. Okay, so there's actually 3 steps in this computation. The first step is going to be this one, which is going to be squaring the matrix element. The second step is going to be integrating. The third step is going to be summing. Okay, so let me do it very quickly. Okay, so I forgot to mention the phase space integration is nothing scary. It just looks like this. So for every soft particle labeled by A, we have to integrate over its free momentum, which is already on shell, with some usual measure factors. Okay, so when it comes to squaring, basically what you're doing is that you have some, the way to visualize cross sections always is to think of it as having 2 scattering amplitudes. One is the original scattering amplitude, and the other one is the complex conjugate star. That's because we compute the absolute value. Okay, and then, for example, the term in which A is equal to 1, so we have exchange 1 soft particle, is associated with, between having the leg I in here and leg J in here. I'm just going to exchange a soft photon. Okay, so this term illustrates the term A equals 1. Okay, and how can this be done? Well, in a sense, we already have all the ingredients, because we talked in the last lecture about the multiple soft theorem. So in fact, we know the expression for this factor in here. These are all soft factors. So what we can do is use the soft theorem, multiple soft theorem, to actually evaluate this sum. Okay, so I have a product of all the soft stuff, LSD, so this is the statement of the soft theorem. I just multiply the soft factors for all the particles. And now I can use my usual trick. If I have the sum over holistes and I have epsilon and its complex conjugate, I can replace it with the eta function. And what this tells me is that the result is the product of the sum this type. Okay. So this factor might look extremely similar, extremely reminiscent of the factor that we've seen before when we computed the virtual radiation. In fact, it's exactly the same. So after the little step of the integration, let me just tell you the final answer. If you integrate this, you're going to get a factor equal to minus EI EJ divided by 4 pi squared. The real part times this. And that's exactly what we've seen. It's no longer on the board, but this is exactly what we've seen in the case of the virtual radiation. The only difference is the sign. All right. So then what I can do in the last step is actually perform the final sum. So the final sum is going to give me the cross section in here. Okay, so the sum is going to give me this is equal to sum of the soft factors 1 over S factorial, which comes from the ellipse, which is over there, times this factor over there. Once again, I have to sum over all possible external states, I and j, and I get this. Then, because of the soft theorem, multiple soft theorem, what I get after including multiple of those states is just the same exponential multiple times. Okay? So I conclude that my inclusive cross-section is equal to this factor here, which, as you might anticipate, is going to exponentiate into E minus the real part of S, the real part of this, and this is going to cancel with the twice, and this is going to cancel with the exponentiation of the divergences in here because of the minus sign and the plus sign in here. Okay, so what this means is that ultimately what I get is that the inclusive cross-section is just the original amplitude with the cutoff lambda, capital lambda, it's all squared, and all the dependence on the lowercase lambda cancels out. Okay, this result, in fact, has a name. Let me just conclude in here. Okay, so very sorry for rushing the last part. But hopefully the physics story is clear. What happened is that the effect of including these additional states precisely canceled the divergences from including the virtual loops. And the cancellation was between these two factors. And that result in QED has a name. It's known as the Black-Nartzik theorem. Which says that the inclusive cross-sections in QED or scalar QED are finite. Right? And perhaps there's also another lesson. We've seen that the result was finite, so that's great. But we've also seen that we've retained the dependence on the cutoff, capital lambda. So another lesson, which is going to be echoed tomorrow in the lectures on the UV divergences, is that physics of starting amplitudes depends on the scale at which we measure it. So since I'm out of time, in the last part of this lecture, I wanted to tell you about the differences between how the similar story plays out in different theories, in gravity, in QCD, n equals 4 super Young mills, and all that, which is all fascinating. It's all kind of more cutting edge than this as well. So I would invite you to maybe come ask questions afterwards, and then we can discuss that in person. So thank you.
Okay. Is there one urgent question? Otherwise, then we can go for lunch. I think it's prepared outside. Okay. Let's thank Sebastian again.
Thank you.